Okay, so for those three talks I'm gonna give, it's gonna be more like a lecture. So in the last slide talk, I stated two theorems. One is about mapping class group acting on product of quasi-trees, and then the baby version was that hyperbolic group acts on the product of quasi-trees with QI embedding. So I'm going to say some of the ingredients of those two theorems. So today I like to say something about some technical aspects of hyperbolic groups or delta hyperbolic space, which are kind of used for the construction of quasi-trees. Okay. Okay. Well, so one more comment. So hyperbolic groups, when I was a student or postdoc, I tried to learn these hyperbolic groups or delta hyperbolic space, and it's a sequence of definitions and lemmas and propositions, and you can't cover in like one or two lectures, but I just try to go kind of quickly, but also I like to spend some time on a few important lemmas, which not only the statement but also you learn some techniques. Okay, so first of all, hyperbolic groups. So definition, one definition is a group G is a hyperbolic group if it acts on delta hyperbolic space X by isometries properly and co-compactly. So this is one definition of hyperbolic group. So I need more definitions for this definition. Properly, I said it, but let me repeat. Sometimes you say properly discontinuously. So this is namely for any point x and any number r, the elements that maps this chosen point to the ball of radius r centered at that point. So this is gx by the action. Maybe you have many of those. Is a finite set. Okay, so this x minus gx means the distance. Sorry, is at most. Maybe I should. This represents the distance between x and gx. It's finite, then you call it the action is proper. Delta hyperbolic. So delta is some number. That means x is well, in this talk, let's assume it's a geodesic space. Namely, it's a metric space, but also the distance is realized by the length of a geodesic. Geodesic space and any geodesic triangle. So triangle alpha, beta, gamma. So each of those three sides is a geodesic in X is delta thin. So I have to define delta thin. Namely, this one side is contained in the delta neighborhood of the union of the other two. So, okay, by doing this, of course, this beta is contained in, so you can just, beta is contained in the delta neighborhood of union of alpha and gamma is contained in the delta neighborhood of alpha and union of alpha and beta. Okay, so maybe I just made, okay. So there's a thing. So that's a definition. So example of say delta hyperbolic space is hyperbolic plane. This one still you have to argue a little bit. So this one, how do you see? Actually, this is, I say, too thin, too hyperbolic. For example, on some. So okay. So definition is G is a hyperbolic group if there is some delta hyperbolic space. Maybe delta can be large number, but as long as such delta exists, it's okay. So I say this is delta. I keep doing the same. Delta 2 hyperbolic. So to see it, I just briefly say why that could be true. So there is Gauss-Bonnet theorem. The theorem says any geodesic triangle in H2 has area of delta at most pi. Okay, it's because I don't know how familiar you are. This is a Riemannian manifold, and its sectional curvature is -1. And if you just look up the theorem Gauss-Bonnet and apply Gauss-Bonnet, then actually you can see that area of any triangle, geodesic triangle, how large it is, the area is at most pi. So if you try to draw in a ball, it can't be so large, uniformly bounded in the size, and actually you can show that diameter is 1 at most. So that's why I put 2 here. So this implies so this delta, any triangle, is say too thin. Therefore, H2 is too hyperbolic. A tree is 0 hyperbolic. So tree it's simply connected graph. So if you have any triangle, typically it looks like T shape, and therefore, one side is completely contained the union of the other two. So you can put 0 here. Okay. So those two spaces are delta hyperbolic for some delta. Now hyperbolic group example is that, so pi 1, 2 is a hyperbolic group because it acts on the hyperbolic plane. It has if you put some hyperbolic metric on this surface, if you go to the universal cover, it's a hyperbolic plane. It acts on hyperbolic plane, and action is proper, and it's co-compact because the quotient is a closed genus G surface. Therefore, this is a hyperbolic group by definition. And also, for example, a free group, say rank 2, but can be n. So is a hyperbolic group because again it's a pi 1 of this figure 8, and if you go to the universal cover you get this regular tree everywhere. So this is a 4 regular tree, okay, and F2 is acting on this, and this is a quotient, it's compact, action is proper, and this is a zero hyperbolic space, therefore a free group is a hyperbolic group by this definition. Okay, good. Later maybe I'm going to give another definition of a hyperbolic group, but this is one definition using the action. Maybe I just say that okay, so maybe I should have said, so in particular is zero hyperbolic because it's a tree. It's a tree, and also it's a silly example, but any bounded set is delta hyperbolic for some delta. If you have a just bounded set, so if you take delta, little delta to be the say diameter of the space, it's any triangle is delta thin. Okay. So then I put Z is, in particular, Z is hyperbolic, and finite group is hyperbolic, but it's not trivial, but Z square is not hyperbolic. This one you have to argue. So intuitively, you know, and so Z2, as you know, it acts on Euclidean plane, and Euclidean plane is not delta hyperbolic for any delta, because if you draw a big triangle in our Euclidean plane, it can be thick, right? But of course, this is backward. You just let your group act on non-hyperbolic space. It doesn't say your group is not hyperbolic. So this is not a proof, but this is also not so bad intuition. But anyway, so I just take it as mention it as a fact that D square is not hyperbolic. Okay. Now, important notion is a projection. So now, suppose this is delta hyperbolic space, and suppose you have a geodesic. I fix it. And then I define, so given, I define the nearest point projection. Okay. For example, for any point x here, you find a point on gamma which realize the distance from x to gamma. I'm tempted to say like this, but actually maybe there is more than one element, so it's a set like this. Okay. For example, Euclidean plane, which is not delta hyperbolic, but if you have a Euclidean plane, you have a point. This is a nearest point projection. So maybe I use this to indicate this is the nearest point for x to gamma. So that's why I say nearest point, because it can be more than one point. But the first lemma, I'd like to give another example. This is in E2, which is not hyperbolic, but say in a 3t. So this is my maybe gamma, and I don't have to do it this way, but okay. So nearest point projection is easier to draw in the tree. So okay, if you have a point here, nearest point projection is this one, this point. So in the case of tree, it's again 1 point. So here's a lemma. If x is delta hyperbolic, then for any x, diameter of x is at most I don't know, but 100 delta, say. So the point is that it contains maybe more than 1 point, but diameter is uniformly bounded. So you can pretend it's a 1 point for some kind of coarse viewpoint. Let me try to convince you why this is true. Okay. So imagine that it has more than 1 point, like this, in the nearest point projection. Okay. Then I draw a triangle for those 3 points. Okay, first I draw like this. Okay, but this is a delta hyperbolic space, so this triangle has to be delta thin. So I should draw a triangle like this way, or maybe even like that. Looks like this one. So a good picture you can try to draw is like this. Okay, so I try to indicate those triangles delta thin. So this is kind of size of delta. Okay, so now imagine this diameter is large, for example, bigger than 100 delta. Then those 2 points are far away, like 100 delta. So okay, let's imagine this delta is positive. Okay, then something is wrong in this picture. Why? Because this point should be the nearest point from x. But in fact, and this is a geodesic, okay? So, and if this is long, it's better for you. If you like to, you are in x. You like to reach gamma as fast as possible. Then you don't have to go all the way like this. You just get on to here, right? It's closer than this one, okay? So again, I say, so you try to, from the viewpoint of x, you try to find the nearest point on gamma, but this is not the nearest point because you are here, which is pretty close to gamma, but you don't want to go all the way along gamma to here. This is a waste because this is shorter, because it's delta thin. Therefore, this party shouldn't exist for a long time. So this is a proof. Okay? I hope you get this. So this is an exercise. Okay. So this is exercise. Maybe I'm going to make a file later. So
can you just go from like let's say the bottom point on the left is y, then you move toward x along the geodesic by delta,
Yeah.
and then you can reach the other geodesic by delta.
Yeah.
Delta thing. And,
Yeah.
I mean, okay, so you go from, you start from both points at the bottom and move toward x along the side by delta, and they are only delta apart.
Yeah.
You find the path which is way smaller than under delta.
Yeah. Yes.
Contribute.
Yeah. So I'm saying this point is a better choice than this one, because this red geodesic is shorter than this one, because this is longer and this is kind of delta. So this is not in here. So the true picture should look like this argument shouldn't work. So the only possibility is like this, and this is by gamma x. Okay. Right. That's why you have a bound. Maybe you can find a better bound, like 10 delta. But okay. So this is one lemma. You can ask questions for this one, because this is a kind of argument we repeat. Yeah. Okay. Then here is another lemma. Again, x delta hyperbolic. If alpha, beta, geodesics, if diameter of the nearest point projection of beta to alpha is large. Large means maybe larger than, say, 1000 delta, then this projection is contained in, say, 20 delta neighborhood of beta. Okay, I draw a picture for you. Okay. Imagine this is a alpha. You have beta. Okay. So assumption is if you project beta to alpha and large. So I have point P, I have point Q, and say P bar. So by bar I mean this is in the projection, and Q bar, say. Okay, and I'm assuming this is large. You know, that's why diameter is large. So indicate. So oops, this is the nearest point projection, the nearest point projection. So I'm assuming this is larger than delta. Then the conclusion is that, okay, so so imagine that, so this is really, say, the projection of beta. It doesn't have to be a straight line like this or segment, but this is large, and imagine this is red line. It's a projection of beta to alpha. Okay. Then the conclusion says this red part is a projection of beta is contained in the neighborhood of beta. So it can't be this shape. It can't be so far like this. It's saying that actually the picture you like to prove at the end is that actually beta is like this. Okay, and that's how this red line, which is a projection of beta, is going to be contained in the, you know, kind of small neighborhood of beta. So let me prove it. Okay, proof. So for many arguments, you just draw triangles and argue. Okay, suppose suppose this is that red one is large. Then first, so this is a rectangle, so I draw in this line and I see two triangles, geodesic one, this and this. So now this triangle is a geodesic triangle and it has to be thin. So so delta, now I indicate the vertices rather than edges is delta thin. That means this geodesic p bar q bar is contained in the delta neighborhood of p bar union p q bar. Okay, this is contained in the union of this and that by delta thinness. Okay, so but you think about it for a second. So this red one is contained in the union of those, I mean delta neighborhood of the union of those two. But imagine that delta is 0. So imagine that this red one is contained in the union of this. Okay, but remember this is a shortest path from P to alpha. Okay, this is the shortest. If you see it backwards, if you start from P bar to P, it goes away from alpha very quickly. Okay, so it doesn't stay near alpha for a long time. Then it's going to be a contradiction, as like this one. So once you start moving from P bar on this geodesic, you are far away quickly from alpha. Namely, alpha, in other words, alpha is not so much in the delta neighborhood of PP bar. Okay, because this most of the part of PP bar is far away from alpha. So I say actually P bar, Q bar is maybe 10 delta neighborhood of P Q bar. Because this is useless for you. Because this is far from alpha. Therefore, in particular, this is far. Most of the part is far from this red one, except for the beginning part. That means most of the part of red, except near this point, is contained in the delta neighborhood of this one. So that's what I said.
Are you arguing by assuming that the conclusion is false and then contradiction? No. So here, okay, here I'm not assuming anything. Yeah, next step I'm assuming that this is large. But okay, so assume this is large, at least, no, it's not, this is not by the way of the contradiction. This is just I was just confused by how do you know that most of the part of PP bar is far away from alpha?
Okay, I say it again, because it's the shortest path from P to alpha. Okay, because imagine that you have a point here, okay,
say this is 10 delta, but at the same time, for somewhere, this is delta. Imagine this happens, okay? Okay, I'm going to tell you that most of the point on PP bar is far away from alpha. Far means like this one. I mean, if this point is far on this path, but close to some point in alpha, then this is a shortcut for P to arrive on alpha. Contradiction, because this is really the nearest point for P. This is shorter than this. Therefore, if you move on this, you are far from alpha quickly. Okay. Yeah. So. Yeah. So. Okay. Yeah. Let me continue. So it says the true picture is this. Okay. It's thin, but it's thin this way. Okay. I'm just saying that. It's not thin in this way, because then there is a shortcut here. Okay, so this is what I said, but now look at, then also delta P, Q, Q bar is delta thin. So this triangle is delta thin. So PQ bar is contained in the delta neighborhood of the other two, namely PQ and QQ bar. Okay, so this is contained in the delta neighborhood of union of those two lines. Now here I use this is far. Okay. Now P bar Q bar is large. Therefore, this PQ bar, this geodesic, here stay for a long time along alpha, because this is large. So this one stays long time like this. Okay. But now again I use the same logic. So this is the shortest path. So this one is not, first of all, this one is not so close to alpha because it goes away quickly. That means it goes away quickly from this one because this one stays close to the red one. Okay. So I just write down the conclusion and say a few more words. Again, P bar Q bar is contained in, say, 10 delta neighborhood of PQ. No, sorry, PQ bar. So PQ bar. Okay, I repeat. So this is a thin triangle. That means this is in the delta neighborhood of this and that union. But again, this one is useless because this is far. Most of the part is far from alpha. Therefore, it's far from this one. Therefore, this is actually has to be near this path. So that's what I wrote. Now, if those two are okay with you, if I combine them using triangle inequality, so it implies that P bar Q bar is contained in 20 delta neighborhood of PQ. Because this is contained in 10 delta neighborhood of this one, but this one contains this one in 10 delta neighborhood, therefore this one is contained in a 20 delta neighborhood of this one, but that's what we wanted to show. Okay? P bar Q bar is actually contained in the 20 delta neighborhood of beta. You can ask questions. Of course, it's better for me to say that now I take a point here whose distance is something, therefore there is a point here and there is a point here. Using triangle inequality, there is a contradiction. I could do it, but it doesn't help you to understand. So anyway, at least you got a flavor of the argument. Or after the talk, I can talk to you for until you are convinced. So, okay, let me go on. Okay. Setup. G is acting on some delta hyperbolic space, and this is by isometries and property. So I'm not so in particular if G is a hyperbolic group, this is fine. I'm not here. I'm not assuming this action is co-compact because it's not important now. And also, so given or fix an element in G, or assume. Which is hyperbolic on X. Okay, so namely, it's a slight lie, but or you can put it as assumption. Exists a geodesic. Excuse me, you have to say maybe quasi, but I omitted geodesic. So which is invariant by G. Okay, so you really have this infinite geodesic, invariant, and G invariant by G, and G acts on gamma as a translation with translation length. Maybe I write it tau G positive. Okay. So this is geodesic and it's really invariant. So you have Gx, G square x. And this is the translation length. Okay, and the proposition. There exists some number C such that for any element A, either Okay, let me just write and then say something. If you do projection, so now let me write it. It's a diameter. It's not a number of points in here. It's a diameter. So I could write its diameter, but its diameter is at most xi, or gamma is parallel to a gamma. Okay, so this is a claim. This is a proposition.
Professor, in what sense you put the suffix quasi in front of geodesic?
Why did I put quasi?
Quasi-geodesic.
What is quasi-geodesic? What is quasi-geodesic? So, okay, so you can first I say what is geodesic? Geodesic is embedding, isometric embedding of a line or segment to x. This is a geodesic by definition. Okay, so this is a geodesic. Okay, if you remember something from the previous talk, quasi-geodesic is a QI embedding of a line. Or you can say quasi-geodesic is a subset in here which is quasi-isometric to a line. So if you compare, if you have any 2 points here, suppose this is a map, and if you like this one, then this is comparable in the previous sense in the slide. But in many cases, actually, it's okay for you to think that your element really has a geodesic axis. For example, it is true for hyperbolic plane. Yeah. So, okay. So, what are those two possibilities? Oh, I like to say parallel. Sorry. This is not too. This is so maybe I just write in this way. Otherwise, I don't know. Okay. So definition. Alpha and beta are parallel. Then I write like this one. If exists a constant L such that, which way is better? Beta is contained in the L neighborhood of alpha. Okay. So then I say parallel. Okay, it's the same definition for Euclidean plane, right? Euclidean plane, two lines are parallel if they are parallel. Okay, here is L. It is not. If it is not parallel, then it's not this way. So there is no bound, like L. L can be a large number, but existence is important. So also here I say in this way. Okay. Before I prove this proposition, I like to prove a little lemma. X delta hyperbolic, alpha beta geodesic, alpha parallel to beta if and only if alpha is contained in the 20 delta neighborhood of beta, and also beta, so is beta. Okay. So I said L can be any number, but actually in delta hyperbolic space, you can always say 20 delta neighborhood. Okay, sorry. I should say infinite geodesics. Sorry. Okay, sorry. Infinite geodesics is really, for both directions, it continues forever. It's really isometric embedding of R. Okay. So this lemma is not true for Euclidean plane, because it can be, L can be any number. Okay. Yeah. Let me prove it. So proof. So this direction is trivial. No, the other direction. Yeah. Because, yeah, so it just L is 20 delta. So this direction is trivial because, so about this direction. By the way, so you can, it really doesn't matter. So if you can also put this as a part of the definition. So maybe bigger number L, but anyway. Okay. So this is more important. So let me say a few words why this is implication. This implication holds. All right. So what is the picture? This is alpha, and this is beta. Okay. So beta is contained in. Okay. This is a function. This is parallel. That means this one. Okay. So this implies that diameter of projection of beta is infinite. Okay. So it's in the L neighborhood forever. Okay. So it continues. So if you project, you can go as far as you want. Okay. So this continues forever. So and this L is maybe large but fixed. So if you have a point here, where is the nearest point for this point to alpha? It can't be here because geodesic is far away. So somewhere here, and go on. So because of this assumption, and both are infinite geodesic, implies diameter is infinite. Okay. So maybe not the entire line, but nearly. Now apply a lemma. Okay. So maybe, I don't know, not everywhere, but it continues forever. So this is pi alpha beta. Okay. So this diameter is infinite. Now I apply the lemma, which I erase. The lemma, one lemma says if there are 2 points far away in the projection, then this segment has to be contained in the 20 delta neighborhood of beta. Okay, that was a lemma. But these 2 points can be very, as far as you go, as far as you can go far away as much as you like to the right and also to the left. So apply the lemma, it means that alpha is contained in the 20 delta neighborhood of beta. Okay. So that's okay. The other one you can also same thing. So that's the end of the proof. Okay. All right. So with this lemma, I go back to this proposition and its proof. Yeah. So
Any questions? Are you okay?
Is it true that if alpha quasi-trees?
Yeah.
Is it true?
Yes. Yes, but maybe this number becomes larger, but still some fixed number. Yes. Yeah. Yes.
Are we using the assumption that there exists a gamma such that gx and gamma as a translation? Are we using that assumption?
For lemma? Lemma? No. I'm just using, there is no group element, no group action here. Just delta hyperbolic space to infinite geodesics. Yeah, not yet. Okay. So proof of a proposition. This one. Oh, by the way, so what is the picture? So you have gamma you started with. So, and you move around by your group element in a group. So one possibility is that they are parallel, but by the lemma, if they are parallel, they stay close, very close. So one possibility is this. This is a gamma. That's one possibility. The other possibility is that a gamma is here, and if you project, it's so this is uniformly bounded by XC. Okay. So either they are parallel, or you project, you only get this kind of tiny portion. So in other words, there is no element A gamma which is not parallel but has a very large and larger projection. Okay. If there is no group action, you can just write, I mean, any geodesic close to gamma stay for a long time but diverge, so they are not parallel, but also projection is large. But this proposition says if you have the collection of geodesics from a proper group action, then that doesn't happen. Okay. So proof. Suppose pi gamma, a gamma is large. So I have to decide how large. So I decide later. In particular, much longer than translation length of, of G. So what is the picture? So this is gamma. So and then I like to say that actually gamma and A gamma is parallel, are parallel. That's what I want. That's a logic. I didn't specify Xi in advance, so it's a bit logic is unclear maybe. But I'm going to argue that if the projection is large, actually they are parallel. Okay. So so this is a. Okay. Remember, this projection is large. Then actually they stay close in the 20 delta neighborhood. Okay, that's what lemma says. Now I take a point P here, say, and this is action with G. Okay, so you have GP, G square P, etc.
So you have many points. You have many points because this is large, much larger compared to the translation length. You have many, many points in the orbit of P.
In the proposition, the gamma is non-arbitrary geodesic, but the axis of some element in the group.
Yes, yes, yes. Yes, this is a setup. Yes, this is a setup. I fix one axis for some element, just one. Yes. Sorry. So yes. So proposition maybe start from here. I should have said some little fact. So one fact: A gamma is an axis for A inverse. Because if you apply A inverse, A gamma, then this is A G gamma, which is A gamma. Okay, so this is A G plus, and also translation length is invariant by taking conjugate. This is also another easy fact. I'm cheating a little bit here because this is axis, so the translation, in particular I'm saying, so maybe A gamma, if I let the A inverse act, maybe the direction is opposite. Okay, it's invariant, but maybe, so G is shifting gamma to the right, but maybe A inverse is shifting A gamma to the left. But let's pretend it's the same direction. So now I take a point Q. I'm tempted to say this is a point P, but anyway. So now this point is A inverse Q, and this point is A G. This is the square of this, but it's a conjugate, so Q, etc. Okay? Those are the points you have. Now, maybe I go over by a few minutes. So, claim is that A inverse minus N Gn of P minus P is at most like 100 delta. Okay, so what does it say? So I start with P, I apply Z to the N for a while, and then I apply AGA inverse minus N to that point P. So it starts shifting back, and I apply N times both. So you end up with a point near P. Okay, so to be safe, I say this is 100 delta. Okay. So as long as this N is small enough for you to, for P to stay in this this parallel region, if you go back using this action, you come back nearby. So this is so any N, say bigger than N and L. So this L depends on how large this projection is. Okay, so that's because I didn't choose C yet. So okay, so for very large L, so you go and come back, and you have this. Okay, now use properness. Okay, so there should be only finitely many elements which does this to you. So only finitely many elements. But N can be between any number between 0 and L. So eventually, two elements in this form has to coincide. Okay, by properness exist N and M less than L, so that AG A inverse minus N Gn equal to AG A inverse minus M Gm as a group element. because there are only finitely many of those pigeonhole argument. Okay, so if I write it this way, another way is G minus N A inverse Gn is a G minus M A inverse Gm. And now I cancel A here, and I move this one to Gm minus N A inverse is A minus M Gm minus N. Okay, I get this. Okay, I cancel A, so I move this to here and move this to here. Okay, and then I move this here. So A, and now set this one. Okay, so then I found this way A Gn is Gna, namely a Gn A inverse is Gn. Okay, so G to the n and A commute. I'm almost there, I hope. So now gamma is an axis for Gn, because gamma is axis for G. So I apply G to the n. Gamma is also axis for G to the n. But a gamma is an axis for a G and A inverse. This is a property I just used. Okay, if I fit by A, right? But actually, I know that A Gn A inverse is Gn. So, namely, both gamma and A gamma are axes for the common element. Okay, now you have two axes for a common element, then you can show that they are parallel. Okay, so this is the end of the proof, and I put it as an exercise here. So this is exercise. So if alpha, beta are axes for a hyperbolic element G, then they are parallel to each other. So parallel to each other, you use this definition, there you find some number L so that one is in the L neighborhood of beta. Okay, in that hyperbolic space, you get this uniform bound. Okay, so I show the proposition. I didn't exactly finish what I was planning to finish, but I think I stop here.